I think we are recording. Yes. So what we are going to do today is we are going to focus on finding roots of an equation. What is root of an equation?
What? Value.
What?
Like a root is like the nth value or something, like the element of the equation.
It's an element of the equation, more or less. But root is when you have a curve, when you have a function. Whenever that function becomes 0, that's your root, right? So if you have a curve, wherever that curve hits the x-axis, that's your root. So if you have something like this, and I'm trying to record this as well, the majority of today's is not going to be on the computer, so the screen wouldn't help you much, but the camera is recording, hopefully. So when you have a curve like this is a root, right? Wherever the curve hits the x-axis, the value of that function is 0, right? So that's the root of your function. How many roots does this function have? 3 roots. Perfect. So what we are going to focus today is focusing on finding the roots of an equation. There are a couple of different approaches that you can take. One approach is called bracketing. With bracketing, what we'll do, well, before going to bracketing, let's have a look at what happens when we have a root. So we are positive with the function values, right? So your function values are positive here, and then goes negative, right? And negative here, then goes positive. Positive here goes negative. So you see the shift of sign, right? From positive to negative, from negative to positive. That's where the root happens, right? Does it make sense? You're positive, you're going negative, you hit that x-axis, you hit that 0. Positive, 0, negative. And then negative, 0, positive, right? One approach to find the roots visually is bracketing. What does it mean, bracketing? It means that break your domain into several points. That's a subjective value. You can go with 10 points, you can go with 20 points, etc. But break it. This doesn't work. This was supposed to be a new one. Break your domain into several points. So for this point, the value of the function is positive, isn't it? For this point, the value of the function is positive. For this point is positive, 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 and then all of a sudden negative, right? Going from positive to negative is where your root resides. Does it make sense? So that's one area that you have a root. And then negative, 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 there's no root. Negative, positive, there is another root. Right? And then positive, 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 nothing. Positive going to negative, there's another root. And then negative, negative, there's no roots. So that's one way to find roots. But what are the problems with this? What are the issues with this method? First of all, how many points do you want to evaluate? Right? You don't know. If you go with 1,000,000 points, then your intervals are going to be very small, very close to the root. If you go with 3 points, then your intervals are too big, right? So you don't really know how many points you want. You can always evaluate it for more number of points, but more number of points means more computational demand. computational cost, because each time you run a function, there is a cost for it. There's a computational cost for it, right? That's one thing. The other thing is it doesn't give you an exact value of the root. It just gives you an interval where the roots is. Can you imagine another problem that we might have if we don't have enough number of intervals? What is that problem, Adam? What's the problem?
No problem.
No problem. Can anyone imagine what would happen if we don't have enough number of points?
It wouldn't come to a point where it's flipped from positive to negative.
Yes. So what happens if we have oh man. What happens if we have this function? And if we have 3 points, or 4 points, or 5 points, is it positive here? Is it positive here? Do you expect any roots to be between them? No, but you have 2 roots, right? So if you don't have enough number of points, you might miss some of the roots. Does that make sense? Perfect. Not only that, what if you have an asymptom? And then you have these points. So at this point, this is positive, right? At this point, it's negative. Should we expect a root? We should expect a root. We are going from positive to negative. We should expect a root, but this is not a root. That's another problem of this function. So there are some problems, but again, that's one approach to solve this. So this is called bracketing. The next approach is called bisection. And it's going to get a little more interesting in a couple of minutes, as I'm going to ask you to write a while loop with the Newton's method to find the roots of an equation. And Danny is all for it, right? So excited. Yes, let's go do while loops. The other method is called bisection. What does it mean? You have a domain, and let me start with a function that doesn't have an issue, and then we'll get to the functions that will give us issues. So we have a domain. We divide this domain by 2. Let me start with a very simple function, actually. We have a domain. We have a curve. It has one root. It hits the x-axis once. We divide this domain by 2, right? Positive here, negative here, right? So the root is going to be between positive and negative, right? Ignore that. Now you have your domain as this, divided by 2, positive here, no root. Positive here, negative here, root. Divided by 2 again. Positive, no root. Positive, negative, root. Divided by 2. Positive, no root. Positive, negative, root. Divided by 2. Positive, negative, there is a root. Negative, no root. Divided by 2. as you can see, it's going smaller, smaller, merging to the root, right? So that's how you can find it. When are you going to stop? What is your criterion to stop? Say louder. Number of elements can be, but that's probably not the best one. So if you set the number of elements at 5, then you probably have a big interval. They didn't merge to one another. When they merge to one another, what happens?
They come close to the same number.
The difference between the two becomes so small, right? Remember that statement in front of the while loop? That's the same thing. So the two will merge to one another. The other criterion that you can imagine is that when we have a root, if this is my function, negative x, this should become 0, right? So the value of the function, if it is too close to 0, that's another criterion to stop. Because root means the value of the function should be 0, right? That's the definition of root. So if f is equal to 0, that's when you hit the root. So that's called bisection, and that also comes with a suite of problems associated with it. One of them is when you have a function like this, when you have a problem like this, your domain is this, you divide it by 2, positive, positive, so no root, positive, negative, there is a root, and then you will merge this root. And you miss these two because they're both positive, right? So you missed a couple of times. That aside, in terms of the stopping criterion, when you say, you know, f is 0 or f is very close to 0, that's when I stop. What if you have a function like this that comes really, really close to 0 and then stays really, really close to 0? Then any points in this interval would fit within your condition of being a root. That's another issue. So that's called the bisection method. But there is another method as well to find the root. This other method is called Newton's method. And then Newton's method is one of those iterative approaches. What you do, you'll have x new, and you will have x old. What is f of x old? What is f of x old? What is f in the first place? Function. So the function that we want to find the root of is f. That's your function f. F of x old is the value of the function at x old. What is f prime? The derivative of the function. the value of the derivative at xo. So now, how do you think we can, what can we do to find the root? What is the procedure? This is very similar to the Newton's approach that we had before, right? To find the square root, do you remember? So how do we do this? We start with some x old, some value, whatever. Find x new, put x new in x old, find another x new, put x new in x old, find another x new, until the difference between the two is very small. So basically the two merge together. Now with this, let's find the roots of f equal to x minus x to the power of 1/3 minus 2 between 0 and 10. Just to jog your memory about the inline functions, let me quickly define inline function and I'll let you solve this question yourself. So I define my function f, as an inline function. Do you remember inline function? Inline x minus x to the power of 1/3. So I put 1/3 within parentheses. Why do I do that? What do I put 1/3 in the parentheses?
Otherwise, you just take the square root of, or the root of 1 and divide that entire thing by 3.
If I don't put this parenthesis over 1/3, it will raise x to the power of 1 and then divide that by 3. So that's not going to be x to the power of 1/3, that's going to be x divided by 3. Does it make sense? The other thing that I want to do, I want to put a dot here, just in case I wanted to evaluate my function for a vector, for multiple points. I put a dot here. So that's my function. And what I can do here, if I do f of 2, it's basically plugging 2 as x into that function. F of 2 will be negative 1.2599. So that's how I define my function. For derivative, we're going to find the derivative first and then define it as another inline function. What's the derivative of this function? F prime. What's the derivative of x? 1. What's the derivative of x to the power of 1/3? So I keep the negative sign here. What's the derivative of this? I'm hearing 1/3 of x to the power of negative 2/3. So 1/3 of x to the power of 1/3 minus 1. Does that make sense? X was what? 1. 1 times x to the power of 1 minus 1. X to the power of 0 is 1. So 1 minus 1/3 of x to the power of negative 2/3. What's the derivative of 2? 0. Done. So f prime, I will define it as df is equal to inline of 1 minus, again, 1/3 within the parenthesis times. Do we need the parenthesis here? Let's define it first and then we'll discuss whether we need a parenthesis or not. Do I need the parenthesis over negative 2/3? Absolutely, yes. Do I need the parenthesis over 1/3?
Yes.
I have yes and no right next to one another. Who says yes? Who says no? Who says that I need the parentheses? Who says I don't need the parentheses? We got 3, so democracy wins. We don't need it. Why? Because 1 divided by 3, and then we have multiply, right? Divide and multiply have the same rank. So it first does the divide. So it first does the divide, then multiply. Now, power has a higher rank compared to divide and multiply. So it will first do the power. What happens is that it will first do the power and then do the divide. So it will, if you don't put the parentheses over, it will first raise x to the power of -2, done, and then divide it by 3. So that's why we need a parentheses over here. We didn't need that over 1 over 3. Does that make sense? You can always use parentheses, it wouldn't hurt. But if you don't use it, it will hurt. So that's now my f prime defined as df. I can evaluate df again at 1, and that gives me 0.6667. Yes?
This might be a silly question and maybe obvious, but if you do df inline and change those variables of x to say something like y, does it automatically do df of y?
It will do df of y, but it doesn't matter. Because when you plug 1 will go to y. So you have a function. The function is correct. The name of the variable is y. What you care about is y equal to 1, y equal to 2. So what that name of the variable is doesn't really...
Yeah, I'm just curious if they automatically just assume...
Yes, so if you just plug y instead of x, you will have df of y. Let's do this. Wouldn't change anything for you, it's just the name of the variable is different now. Does that make sense? All right, so let's do this. I'm gonna stop the recording, and I'm gonna give you some time to zoom. Perfect. So let me open up a new script. In the new script, let me just define my functions very quickly. F is equal to whatever that was before. So I define my functions, right? In order to start the while loop, I need x new and I need x old. So I just define them as 2 values. Let it be 2 and 5. 0 is not a good starting point. 1 is not a good starting point. Let's avoid them. 2 and 5, 10 and 15, whatever you call it. We want these two, x new and x old, to merge to one another, right? If we want them to merge to one another in the while loop, we don't say while they're equal to one another. Reason for equal is that when you say equal, let's say they merge to 2, both of them should be 2. If one of them is 2.000000, I don't know, 10,000 zeros, and 1, that's not equal. Right? Yes?
Is there any reason why you have x new and x
I have x old and x old. X new and x old, sorry. Was that a question? Yeah, that was it. So if you put them equal to one another, it's going to take probably an infinite number of iterations for them to be equal, right? 2.00001 is equal to 1 for us numerically. We don't really care about that small difference. But if you set them equal to one another, it's going to take forever. Does it make sense? Everyone? Perfect. So when you define your while loop, your statement is not going to be while x new. If you want to say, if you want them to become equal to one another, that's your statement, right? While x new is not equal to x old, keep running. When they become equal, it will stop. But this is going to take forever. Again, because of that reason. 2.00, 10,000 zeros, 1 is not equal to 2. So instead of using the equal sign, we use while their difference is more than a small number, 1e negative 4, for example, keep running. There is an issue. What's the issue here? Absolute value. While the absolute value of the difference between the two is more than 1e negative 4, keep running. What will you do? You put x old equal to x new.
No x new equal.
Not x new equal to x old. This is wrong. X new equal to x old is wrong, right? You put x new into x old, you calculate another x new. You put x new into x old, you calculate another x new. If you put x new equal to x old, they will, in the first iteration, they will become equal to one another. Let's see how. Then your equation is so let's see what happens if we have x new equal to x old, right? You start with 2 and 5, you come here, x new becomes x old was 2, x new becomes 2. Then you have x new equal to x new, which is 2 minus f of x old, which is 2, divided by df of x old, which is df of 2. So you calculate some x new value. You go back. X old is still what? 2. We haven't changed x old. So x old remains 2 forever. So you're basically doing a loop without any reason. X old is still 2. You calculate the same x new each time. Does that make sense? So x old equal to x new. Then the other thing is, you don't put this after this. Reason for that, you calculated your x new, let's say 3.7. You put 3.7 into x old, so you have x old equal to 3.7, you have x new equal to 3.7. It comes here, are they equal to one another? Yes. The difference is 0. 0 is more than 1 in negative 4? No. Just comes out right at the first iteration. So that's your this 3.5214 is your root. In order to see the root, you can always plot this. X is equal to linspace between 0 and 10. And then plot x comma f of x. That will give you nothing. If you evaluate it, that will give you the plot. Now, wherever this graph hits the line 0, that's where you have your root. And then to see that line 0, you can always do grid on. If you do grid on, let's see what happens. It will put these grids for you, and then you will see, all right, so I want this to be 0, and that's about 3.72 or so that it becomes 0. See? This is when it becomes 0. So that's how you visually see your root. Yes?
So in your function, you have x nu equals x nu minus f x old,
Uh-huh.
but on the board, you have x.
Oh, okay, so that's x old minus.
Okay, yeah. Because you get the same answer.
You get the same answer.
Okay.
That's the iterative process. You get the same answer.
Also, how does it work when you do x equals 1 space 0 to 10 afterwards? Is that just like for the graph?
That's just for the plotting. So that linspace thing is only for the plotting. And then when you do f of x, it will evaluate f at all those x values which are linspace. 100 values between 0 and 10.
And everyone has to get the same number that you got?
Yes, 3.5214.
2.3.
You got 2.3. All right, so you made a mistake somewhere. But let me finish up today. I wanna cover everything. So next session we only do homework. I don't want to cover new material next session. The other method, the issue with this is, first of all, if you have several roots, it will only give you one, right? It will give you one root. If you have several, it will give you one of them. How can you get, if you have several roots? Let me do the other function. Clear CLC, get rid of everything. F is equal to inline of x squared plus 2 times x minus 10. So that's my function. df is equal to inline. I'm just going to take the derivative here. 2 times x plus 2, right? That's my derivative. And then let me plot this function first and see how many roots do I have in the first place, between negative 10 and 10. X is linspace between negative 10, bless you, and 10, and plot x comma f of x. And let's do grid on so we see the line 0. So the line 0 is here. I have one root over here, one root over here, right? If I just copy and paste what I had before, let's see what I'll get. I'll start at 2 points, 2 and 5, and I will keep doing the same loop until I find the root. F and df are now different, right? With the new problem, I have new f, new df. So basically, this is finding the root for the new function, right? Starts at 2 and 5. We don't care about the starting points. I get 2.31, so I get this root. But I didn't get this one, right? What?
That I got 2.31 then the
Okay.
problem before. Is the same?
Maybe you defined this function for the problem before.
Oh,
So you are one step ahead of the class.
I know.
So we found this one. How can we find the other root? How can we find the other roots? Any idea to find the other roots?
So like having the graph.
We want the exact value.
Is it have something to do with the absolute value?
Not the absolute value.
Would it be to change your f and df to negatives?
You cannot change f and df. That's your function and your derivative. What else can we change? Yes.
Change where you start your x new and x old.
Absolutely. So you started with 2 and 5, you ended up here. You started with -8 and -6. You'd most probably end up at the other one. So let's change them. Well, let me copy and paste them because I want to keep the previous one. Let's change them to -6 and -8. And you will get the other root right here, 4.3 something. Does it make sense? So you can play around with these starting points to get all the roots that you have. Are you clear with this? Now the issue with Newton's method is that you will need this f prime, right? You will need a function for the derivative. So you need to find the derivative of your original function. What if your original function doesn't have a derivative? What if your original function doesn't have a derivative? You cannot use Newton method, can you? No. But you can always approximate your derivative. F prime is equal to fx plus delta x minus fx divided by delta x, isn't it? Do you remember this? If delta x merges to 0, this is your f prime. Do you remember? Of course not. No? Derivative means local slope, right? Local slope means what's the change between the function divided by the change between the x. So if you have this is your delta y, which is f of x plus delta x minus f of x. This is your delta x, which is basically x, I don't know, x mu minus x old. Does it ring a bell? That's f prime derivative, or this. Now, this is a numerical approximation for f prime, isn't it? We can replace f prime with this numerical approximation. But to make it a little easier, we'll do f of x nu minus f of x old divided by x nu minus x old. This x nu minus x old is delta x, and x nu is x plus delta x. Does that make sense so far? So our function here, or our our estimator of x nu and x old should change. Now we have x old, we have x nu. We want to calculate another x nu, so x nu nu. Is it confusing? Let me write the equation, and then maybe instead of x nu I should use x middle, not to confuse you. So now, instead of having x old and x new, we have x old, x middle, x new. X new is equal to x old minus f of x old. We had df of x old, didn't we? We replace that df or f prime of x old with this f of x middle minus f of x old divided by x middle minus x old. So basically we removed that f prime and used the numerical approximation for f prime. The only difference is, instead of having x old and x mu, I have x old, x middle, and x middle. That's the only difference. Now, this is called secant method. Basically Newton method, but numerical approximation. So what I will do, I will copy and paste whatever I had before, and now use secant method for it. So I copy and pasted whatever I had before for that, for the second function, x squared plus 2 times x minus 10, and then I don't want to plot it again, so I just remove that. I define x old as 2, x middle as 3, and x new as 5. While absolute value of x new minus x old is more than 1 e negative 4, now the difference is you put x middle in x old, you put x new in x middle. That makes sense? And then everything else is the same. Instead of df, we have that new thing. We have f of x middle minus f of x old divided by x middle minus x old. You don't have to memorize these equations. I'll give the equations to you in the exam if necessary. If I just evaluate this now, you will see that I will get the same answer as before. But now the only difference is, let me put all these into one line. The only difference that you see here is that instead of having x old equal to x new, we put x middle into x old, we put x new into x middle, and then we evaluate this function to calculate the new x new. Does it make sense? We only basically removed, yes?
As far as the value goes for the negative side, would we again just change all three of those values?
Exactly. So -2, -3, -5. Evaluate it again. It will give you the other.
What happens if we have, like, our values are outside of the range? So we know that the, like, negatives is -4.3166. If we were to have, like, x old was 4, or 5 rather, x new was 7, x mid was 5. So that
as long as they are not equal to one another, that's fine. So you put them 7, 5, and 9. It's okay.
Okay, so it doesn't have to be within the range.
No.
Okay.
It will get you to the destination as long as they are not the same.
Mhm.
Does this more or less make sense? We just remove that f prime and put the numerical approximation of f prime. That's about it. Nothing else. We have 5 minutes. I have to cover 2 functions. Now built-in functions. Way easier than this. There are built-in functions that will give you the roots. So basically didn't have to write all those secant, etc. I CLC and cleared everything, so they are all gone. I define my function again, f equal to this. The built-in function that will find the root for you is called f0. f0 of my function, comma 2, will give me 2.3166, which is the root. f0 is a hybrid method. That's a built-in function. You can use it. f0 of your function with a starting point will give you the root. If you want to get the negative side, f0 of f comma negative 2 takes you to the other one. Just starting at the positive point doesn't mean that you'll always get the positive root. You'll have to play around with the starting point to get all the roots. Does that make sense? Just play around. Put it as 2, put it as 5, 10. Yes. In just a second. So that's the function f0. Does it make sense to you, Joe? What? Oh, sorry. f0 is the built-in function to find the roots. That's a hybrid method. It uses the bisection, it uses Newton's secant method, and a couple of others. It's in the background, already written built-in function. You can just evaluate it. That's one thing. For polynomials, do you remember polynomial? X squared plus x minus 10. X to the power of 3 minus x to the power of 5, etc. Integers, right? Integer powers. For polynomials, you can use the function roots, R-O-O-T-S. When you use the function roots, for this polynomial, we have 1, we have 2, we have negative 10 as the inputs. So if you do roots of 1, 2, and negative 10, it will give us both the roots. This is only for polynomials. If you have a polynomial like this, x to the power of 5 minus x plus 10 or plus, I don't know. Well, let's say my function is this, x to the power of 5 minus x. How do I use function roots?
1, 0, 0, 0.
Roots 1, 0 for 4, 0 for 3, 0 for 2, negative 1 for 1, well, need space between them. And then 0 for that intercept. It has complex roots. Does it make sense? So f0 and roots are the two built-in functions that you can use to find the function roots. What we'll do on Friday, we will work on your homework in class. The homework are going to be some real problems from other courses that we will work on and use f0 and other methods to solve.